The concept of a strictly dominant strategy is a strategy that guarantees a higher payoff for player I than any other strategy available to player I. And this regardless of what other players are doing. So the utility for player I of strategy SI, given what other players are doing, is greater than the utility associated with any other possible strategy for player I S prime, given the same profile of strategies played by other players. And this is true, of course, this is true for all other strategies played by, this is true regardless of the profile of strategies played by the other players. This set here, capital S negative I, is simply the set of all possible strategies played by other players. Okay, so in this case here, SI here is a strictly dominant strategy. You get a higher payoff by playing this than any other strategy available to you, and this is the case regardless of what other players are doing. This is true for all possible combinations of strategies played by other players. That's a strictly dominant strategy, and if you put in a weak inequality sign here, you will get a weakly dominant strategy. Okay. Now the concept of a strictly dominant strategy, there exists a strategy is dominated if there exists another strategy as prime I, okay, which is available to player I, such that for all set of possible strategies played by the other players, the utility of S prime I, given what these other players are playing for player I, is greater than the utility of strategy SI, given what these other players are doing. And this is true regardless of what these other players are doing, because this is true for all combinations of strategies played by the other players. In this case, SI is dominated, right? It's a strictly dominated strategy because there exists another strategy which is such that you get a higher utility no matter what. I should point out here, I've forgotten to put here that this is up here. This is true for all S prime I element of SI. Right. Okay. So the concept of strictly dominated strategy is very important. For all strategies possibly played by other players, there exists another strategy available to player I that has a higher payoff than SI, and that means that SI here is strictly dominated. And if we were to put loosen the inequality sign here, of course we would have weakly dominated strategy as well. Okay, so now we have outlined some conceptual apparatus. We're ready to start applying these concepts, because dominance is a way to answer the question of what will not happen. So it's being used as a solution technique. So what we're doing is we're going to be eliminating strictly dominated strategies on the basis that the player is rational and the other player knows that he is rational. So we have this iterative deletion of strictly dominated strategy that follows this strong assumption of rationality. So let's look at what this looks like. So here is an example of a game taken from a short book by David Krebs called Game Theory and Economic Modeling. This is on page 27. And here there is a way for player B to predict that player A will never play strategy X. So strategy X is strictly dominated. And in this case, it's strictly dominated by strategy Y, because regardless of what player B does, the payoff associated with strategy Y for player A will always be greater than the payoff of strategy X, right? If player B plays U, then 5 is greater than 3. If player B plays V, 8 is greater than 7. So the payoff for strategy Y is always greater than that for strategy X. So player B can eliminate strategy X as being a strictly dominated strategy. But now once you have done this, there is no way to continue to further delete strictly dominated strategies. If you now focus on player A, knowing that player B knows that player A will never play strategy X, is there anything that player A can do? So as it turns out, there is no strategy of player B that is strictly dominated. The payoff for playing strategy U here is greater. Well, if A plays strategy Y, player B will want to play strategy U because 1 is greater than 0. So player B plays U. But if player A plays Z, player B will want to play V because 2 is greater than 0. So neither U nor V is a strictly dominated strategy, and the iterative deletion ends there. Now consider this version of the game. Player A's payoff have not changed, but player B's payoff are changing slightly. The 0 here is now replaced by a 2. So this is a slight revision to this game. B can still eliminate X, but now we can continue further eliminating U, because strategy U now is strictly dominated. Why is strategy U strictly dominated? Because regardless of whether A plays Y or Z, the payoffs to player B is always going to be greater with strategy V, because 2 is greater than 1, 2 is greater than 0. So this example shows you how this slightly revised version of the game can actually lead you to continue and proceed with this iterated deletion of strictly dominated strategies. So this, in this case, can actually lead to an outcome where we can solve the game. We can solve the game and say that this is going to be the play. Because now, given that player B plays U, we know that player A will play Y. And that's because 8 is greater than 6. Right? Now, the assumptions that we need to get there are, to be able to solve this game, are, first of all, A's rationality, B's knowledge of A's rationality, and B's own rationality, in terms of taking into account that knowledge of A's rationality. So we have these kind of hyper-rational agents who know that the other players are rational and who are rational themselves, and on that basis rule out certain actions on the part of the other players. And we could continue this process of iteration and deletion, but it requires each time deeper and deeper levels of knowledge, right? So we could even define the kind of the level of order of common knowledge which is required as this process continues. Now this is the classic version of the prisoner's dilemma from our textbook, Mascolo, Winston, and Green, on page 237. And you can see that the strategy to not confess is strictly dominated for each player. because -2 is worse than -1, -10 is worse than -5. So for player 1, regardless of what player 2 is playing, the strategy to not confess is strictly dominated and will not be played. And for player 2, the same holds. -2 is worse than -1, -10 is worse than -5. And so the strategy to not confess is also strictly dominated. Note here that there is no iteration. Both players, we can basically eliminate. We can solve the game by eliminating strictly dominated strategies, but we don't need to rely on each player's knowledge of the fact that there are strictly dominated strategies for the other player. The other interesting outcome, of course, is that the solution for this game that emerges is not a Pareto optimal outcome. The solution to not confess for both players is a Pareto improvement, but it's not rational for the players to get to this result. Assuming, of course, that you endorse or embrace the framework of game theory, which is this arguably narrow view of rationality, but this is better discussed in Sanjay's lectures, and we'll return to this point. Now, in this version of the game, of the prisoner's dilemma, there is no such way to immediately, there's no such way for player 1 to immediately remove a strictly dominated strategy. And the reason for this is that the outcome of not confessing here, 0, is actually better than -1, right? So if player 2 were to not confess, play the strategy of not confessing, then player 1's would play don't confess. If player 2 plays confess, then player 1 will play confess. So the strategy of not confessing is actually no longer strictly dominated, but we can still solve the game through an iteration. The first thing to note is that focusing on player 2 will actually be able to eliminate for player 2 the strategy of not confessing, which is strictly dominated. And the way to see this is simply to observe that -2 is worse than -1, -10 is worse than -5. So regardless of what player 1 does, player 2 will never play don't confess. And once you've done that, now you can eliminate not confess for player 1, because -10 is worse than -5. And you've already eliminated the strategy of not confessing for player 2. So now you come to the same conclusion for this game. You have the same predicted outcome, just a slightly different way of getting there. Here we rely on the knowledge of player 1's knowledge of player 2's rationality, player's 2 rationality being to not play the strategy of not confessing because it's strictly dominated.